And second thing is that next Monday will be our first quiz. So later I will make an announcement in the cameras. So please be aware of the notice in cameras. Next week, next Monday will be our first quiz. And the range of quiz will cover all the topics we discussed until that quiz. So that include probabilities, expectations, Barris, Bayes rule, and also the content regarding today's lecture and Wednesday's lecture. So you can begin to prepare your quiz right now. So just a kind of reminder, according to our call syllabus, in case that you won't go through it and you didn't listen carefully in our first class, actually among your quizzes and final exams, you are allowed to take a cheat sheet. We have some cheat sheet. But for quiz, you can take one single-sided cheat sheet, meaning that in a A5 letter, you can write down all the formulas and equations which you think beneficial to that might be beneficial to your quizzes. But you can only write in one side, you cannot write on two sides. The two-sided cheat sheet are only allowed in the final exam. So you can prepare for that. But during the quiz, you're not allowed to use calculators, cell phones, books, or any other electrical devices. And don't worry, you are not required to compute those tedious numbers. It will be very easy to compute. You won't need some calculator. So yeah, I will make this announcement on cameras after the class. So like you can skip today's class, you can skip Wednesday's class, but don't skip next Monday's class because there is a quiz. Unless you want to give up the score of the first quiz. According to our policy, among all the quizzes and the homeworks, we would automatically drop the lowest score. If you skip one quiz, meaning that your lowest score will be 0. Well, it is automatically skipped. Any question about quizzes and relative things? And then you have emergent things to do, like you have to skip that class due to, for example, you have to go to the hospital. After that, please send me a document showing that it is some reason you have to skip the class. And then we may schedule a make-up exam, a make-up quiz. Okay, so let us talk about the course content. So we have finished introducing the Bayes rule. So today, we'll begin to discuss another topic called central limit theory and PAC framework. So PAC is related for probably approximately correct learning framework. So it sounds very hard, but it's actually very intuitive. And later we'll explain what is PAC learning framework. So we'll start to introduce central limit theory. So if some of you have already taken statistical classes or probability classes, central limit theory should sound familiar to you because this is kind of theory which maybe plays the cornerstone of the modern statistics. After you get to know what is central limit theory, you'll get to know why the normal distribution or Gaussian distribution is so important. Why nearly all kinds of statistical classes or machine learning classes will introduce normal distribution and even ask you to remember how to write down the density function. Although it is not, you are not obligatory in this class to remember the equations, but later in your future classes you may request them. You may be asked to remember it. So, and then starting from central limit theory, we want to introduce the problem that how can we quantify or how can we make some guarantee about the learned models from some data set. And you will find that because the data set you collected from real world are actually random and noisy, it is not deterministic. That means you cannot place some intuitive guarantee like after some powerful algorithm, I can claim that my learned model will have prediction error over all kinds of future examples. Its error is less than some like 0.1. You cannot guarantee this point. And then there naturally leads to a question that would be, how can I give a mathematical guarantee about the performance of your learned model? That leads to the packed learning framework, probably approximately correct learning framework. Because of the randomness of the model, you'll see later. If you want to derive some guarantee about the model's performance, which we call it generalization performance, we have to introduce some probabilistic bound. This is called a packed learning framework. And the implementation of packed learning framework, namely those fancy conclusions regarding machine learning theory, are essentially based on several commonly used concentration inequalities or probability inequalities. And in today's lecture, next day's lecture, Wednesday's lecture, we will go through about 3 commonly used concentration inequalities. But we won't be able to show how you use these concentration inequalities to derive some packed learning results, like when you train support vector machines, what's the generalization bound. That's not the task in this class, but if you register the class, say my class, the next semester, like CS 5350 or 6350, you will see a few of such kind of examples. Okay, so we'll start to introduce central limit theory. To introduce central limit theory, let us look into our common data analytics tasks. So when we perform some data analytics tasks, what kind of things do we have in hand? If we want to perform some data analysis, we must assume we have something, right? Otherwise, how can we do the analysis? We should have data. Yeah, of course. Without all the data, how can we do the data analytics? So we assume that we'll have a data set. Here we still denote it by D. Now that it is a set of data, it means this data set usually consists of more than one single data point. So usually we can denote it as a set of like multiple data points, like x1, x2 to xn. This is pretty common. We can associate with some simple examples. For example, if you want to investigate the chance, like when you toss a coin, the chance of heads, right? And to investigate or to research this problem, what kind of data set do you get? An idea?
A binary set of heads and tails.
Yeah. You can ask your friend, or you do it myself, you toss a coin like 100 times. The first time you record whether it is head or tail, which could be x1. The second could be tail. Third could be like you want to investigate the chance of different points, 3, 5, x4, 1 again, x6, x6 to be 6, and etc. until xn. And third example, for example, you want to investigate the annual income of the families in Utah. The what kind of data set you want to collect before your research? Yeah, ask your families, ask your friends' family. Like you just do the survey in a sample population, right? Say in Salt Lake City. X1 could be my family's annual income, and X2 could be your friend's family's income. X3 could be another one, right? So you collect like 1,000 data points. You have your data set for the research. So this is our common data analytics jobs. So first, we assume we will have some data set, a collected from practical environments, and this data set is not only contains one single data point. It usually consists of multiple data points. And now to analyze the data set, a very commonly used assumption is called IID assumption, which we briefly mentioned in the last lecture. If you still have some impression, we mentioned that under IID assumption, it is much more convenient to compute the likelihood of the whole data set. Right? But we can go back to review this IID assumption again, right? So IID, the full name is independent, identically distributed. So here's IID. So what does that mean? So we're going to look at one by one, right? So first, what does independent mean?
Unrelated.
Yeah, of course. Literally, it's not related, but not related or what? Who are not related?
The events are not. One doesn't influence the other.
You mean one? What are you referring to?
One data point does not have an impact or influence the second data point or another data point.
Yeah, correct, right? So what we're saying, this data set consists of independent or IID. What does it mean? It means those data points are independent. So what does independent mean? Intuitively speaking, they are saying, okay, they have nothing to do with each other. So mathematically, what can we conclude by saying these data points, x1 to xn, are independent?
Probability of x2 given x1 is the probability of x1 times probability of x2.
Yeah. So according to the definition of independent, we say if a set of data points x1 to xn. So here I want to emphasize x1 and xn are random variables. That means when you collect the data set, each data point is just a sample of those random variables. So when you collect the data again, the value for x1 could change. Keep this in mind. So what we're saying, these data points are independent, meaning that x1, x2, and xn are independent. So according to the definition of independent, the joint probability of x1, x2 until xn equals to what?
Production for each of them.
Yeah, production of each of the marginal probability. So this means this data point are independent. And then now let us look at second term, identically distributed. So what does identically distributed mean?
They all the same probability distribution.
Yeah. Just as the name suggested. They mean that, okay, the distribution of x1, x2, xn are exactly the same. Meaning that, okay, x1 follows some distribution f, x2 follows the same distribution f, until xn follows distribution f. So what's this distribution? It could be some, for example, normal distribution with a specific mean and variance. This is one example of this distribution. It could be some discrete distribution, right, which can be represented by a table. Right? So this is the value equals to 1, the probability is P1, value equals to 2, the probability of P2, value equals to 3, the probability P3, and etc. Or it could be some Laplace distribution in your homework. So anyway, we don't make any assumption about what the specific distribution is. We just assume that, okay, each data point, which is a random variable, follows exactly the same distribution. But unfortunately, this distribution is usually unknown. So this is called IID assumption. So this consists of 2 key points. First, the data point, each data point inside the whole data set are independent to each other, meaning that their joint probability is the production of their respective marginal probabilities. And second, identically distributed, meaning that each data point follows exactly the same distribution, which, however, is usually unknown. So now, given this IID assumption, what are we interested in?
Find the distribution.
Yeah, exactly. Given the assumption, we're interested in what will be this hidden distribution. This is our task. And this is the most common used assumption. And in a lot of cases, it sounds very reasonable. For example, in our tossing coins experiments, usually you won't assume that this time, whether your tossing ends up with a head or tail, has nothing to do, has something to do with last time's result or next time's result. Or when you roll the dice, you won't assume, okay, this time when I get 6 in face, and next time I will get another 6. You won't make such kind of assumption. So in a lot of data mining tasks, this IID assumption is quite reasonable. That's why it is very widely used in data analytics. But just keep in mind, there are some cases which violate such kind of assumptions. For example, the temperature. So x1, if x1 indicates today's temperature, x2 indicates tomorrow's temperature, and then 3 indicates like Wednesday's temperature. It is usually not reasonable to assume x1, x2, and x3 are not related to each other. You cannot assume, okay, x1 to be like very hot in summer, right? And x2 will be very cold in the winter. Although maybe in Salt Lake City there are some days such kind of things will happen, but in most cases it won't happen. And in those kind of cases where we do not assume the data points in our data set are IID, there is a branch of machine learning research areas called relational learning. Want to account for the possible dependencies or relationship between the data points in the data analysis. But that's not our focus in this class. And here, in this class, we only focus on the most commonly used assumption, IID assumption. And given the IID assumption, I just want you to keep in mind that there could be other assumptions in data analysis. And of course, when you perform any data analytics task, you must make some basic assumptions. Otherwise, you cannot do the modeling, do the computation. So now let us concentrate on the IID assumption. So given the IID assumption, mostly the task will be to infer the hidden distribution F, where all the data points are following F. Of course, if it will be the perfect thing, or it will be the best thing that we can get the explicit form of F, this hidden distribution. But unfortunately, it's really infeasible. You cannot simply assume F is a normal distribution or some discrete distribution, or some Laplace distribution. Maybe the distribution for F even doesn't have any analytical forms. So generally, we'll step back a little and to look into some properties about this hidden distribution. So if you will take such kind of data analytics jobs, then what kind of properties of F will be interested in? An idea? If I know, okay, there are some hidden distributions which govern the sampling of x1, x2 to xn, such that we can collect this set of data set, right? And now, our task is to find something that can describe this hidden distribution F.
Well, if there's like multiple averages or maybe 2 points so that you get a large bulk of data, that could be useful for the issue.
Your thinking is quite intuitive, but can you give me some terms? The terms which we have mentioned in the class.
I don't know what your signal would be in that situation. So.
Think about it. Actually, we actually discussed this before.
Trying to determine the
Yeah, excellent, right? So now that I don't know what exact distribution will be, actually in nearly 99.9% cases, you won't be able to get the explicit form of this hidden distribution. Now, what kind of properties I want to get from this hidden distribution? First is the expectation. So what will be the expectation of the random variables following this distribution? That is denoted by F, right? Meaning the expectation for F. So according to the definition, it's an integral, right? It's integral over X over the whole sample space of the random variables, and is a weighted average. And here is the probability density function. Obviously, if it's a discrete distribution, then the integral becomes the summation. So this is just the definition of the expectation. So now comes a question. How can we estimate this quantity? How can we estimate the expectation for this hidden distribution F? An idea? So actually, we often use a way which are very intuitive.
Do we just find the average of the data?
What?
Just find the average of the data?
Yeah, just find the average. We can use an intuitive way, right? Like you want to estimate the chance when you toss a coin, it is head, right? How can you do that? You toss it like 100 times, and then count how many heads finally shows up, right? And just divide this heads count by the total count. So in this case, x1 will be either 0 or 1, x2 will either 0 or 1. So this average is just the total number of head count, right? And then divided by total number. So this is average. It's very intuitive.
And what if it's continuous? It's not a discrete number.
Yeah, continuous. You can do the same thing. Yeah, you can do the same thing. So an intuitive way to estimate the expectation of our interesting hidden distribution F is to take the average of all the data points in the data set. This is called sample mean. We define this as sample mean because it's just a simple the mean of the data points. And keep in mind that sample mean is also a random variable. Why? Because each data point, x1, x2, and xn are random variables. So you average a set of random variables, it still ends up with a random variable. So next time we'll collect another data set, select a d prime, you get another set of values for x1, x2, xn. then you take the average, you take the sample mean, your sample mean will be different. Right? So we want to use the sample mean to approximate or to estimate the expectation for the hidden distribution F. So now we're going to ask, because this is a very commonly used method, we want to ask how can we illustrate its rationality in terms of mathematics. Why it is reasonable to use the sample mean to approximate the expectation. Why? First, the sample mean is a random variable, no doubt, right? So first we can check whether the expectation of sample mean is exactly this expectation for the hidden distribution F, right? If the expectation for the sample mean is different from that, there could be some systematic bias. Right? That's not favorable. Then what is the expectation for the sample mean? So to check whether this is a good estimator for the true mean for the hidden distribution F, right? We first want to check whether the expectation of the sample mean is consistent with the true mean. Is it consistent? If it is not consistent, okay, I see, this is not good, right? So now let us check. What is expectation for sample mean? So it is expectation of the average of the n data points. How can we compute this expectation? Let us recall what we have reviewed for expectations, right? So we mentioned that expectation is a very good and very friendly operation because for any two random variables, the summation of their expectation, the expectation of their summation is simply the summation of their expectation. Right? This is the first property. And the second property is that the expectation of a random variable multiplying a constant c. So here c is not random variable, it's constant. Is equal to what?
C times the expectation.
Yeah, we can move c outside expectation, yes. So we can simply compute the expectation of sample mean using these two rules. Right? How can we compute? First, this one, the summation of set random variable, we can treat it as just one single random variable, right? And the one single random variable multiply with a constant, which is 1 over n. So first, we can move 1 over n outside expectation, and turns out to be 1 over n expectation of this. Right? This is summation. And now how can we compute the expectation of the summation for this n random variables? How can we compute? Yeah, use this first rule. Right? So it is straightforward. So it's a summation of their corresponding expectations. And how can we get this, the summation of these expectations? Now we need to refer to the IID assumption. So we know each data point follows the same distribution F. Right? So what does it mean? It means that the expectation for each data point is actually identical because each data point follows exactly the same distribution. So each EX1, like EX1 will be the expectation under the distribution F, right? Because X1 follows F. X2 follows F as well. So expectation of X2 is the F as well. And similarly x3 and xn, and finally for exn, the expectation will be the same. So now the summation of this n expectation is actually to sum the same value ef for n times. Then it ends up with n ef. And now we know that outside there is 1 over n. So denominator and numerator cancels. And finally we ends up with ef. So now we can say the expectation of the sample mean is exactly the expectation for the hidden distribution f. So at least there won't be any bias about our estimation. On average, this sample mean will be the same as the expectation for this hidden distribution f. So it looks like it is reasonable. Then there naturally comes out another question. We know that according to our IID assumption, because each data point they follow the same distribution. So the expectation for any data point will be exactly the same as EF. Now that we check whether this sample mean, its expectation is consistent with the true mean, right? True expectation. But now we know each data point, their expectation is already EF. Why wouldn't we just use a random pick of one data point as the estimation for EF? Why not? For example, let me just random pick up that x2. I simply use x2 to estimate. The true mean of the hidden distribution f. Would that be okay? Why? It's not overfitting. But there must be something wrong here, right?
Like if you were flipping coins, you just pick one.
Yeah. Obviously, from some simple experiments, you can see it's not very reasonable. But if you just check the expectation, you will say, okay, both the estimation with just one single data point and the expectation with sample mean, they have the same properties in that their expectations are all consistent with the true mean. Then how can we differentiate, or how can we compare this sample mean and some single data point estimation x2? How can we use some mathematics to show that this one is better or x2 is better?
Does that have to do with the variance? Like, does that, like if you had no variance, then you could pick any value as the expected value, and then you, in that case, you'd be right.
Yeah, very good, very good. So now we know that by simply computing the expectation of those estimations won't be enough, because even if you random pick out one data sample, you know one single data point, you know the expectation is also our objective. Right? Now to compare these two estimators, we need to check the variance, as you just said. Right? So why checking variance is important? We can consider the case. We're going to try to do some analysis. So now we know that we have two types of way to estimate our interesting quantity expectation for the distribution f, right? The sample mean and some data point x2. Say x2. You can also choose x1, whatever you want. Right? I just want to compare which one is better. At least in terms of the expectation, they have the same properties. They both are unbiased. They on average they equal to the expectation, the true mean. Right? And now to compare them, we want to investigate their variance. Why? Remember, they are random variables. Right? So suppose this is our true value, true mean. Right? So when you collect the data set 1, you end up one estimation, say one sample mean, that could be here. If you collect the data set again, remember this is a random variable, so when you collect data set again, so the value for x1, x2, and xn could change. And correspondingly, you will end up with another different x bar, right? The x mean. So that could be showing up here. Right? And third time it could be here. The fourth time could be here. And similarly for x2, we observe the same thing, right? In the first data set, x2 could be here, and second time x2 could be here, and third time x2 could be here. Right? And then how can we conclude that using any of this quantity is more reliable than the other? How can we conclude that? We want to ensure that on average, these points, whether these estimations are close to the true value, yeah, right? Rather than on average jump very far away. Right? So if the sample mean, like this time is here, sounds pretty good, and next time is here, it's not good. Right? And next time is here, very bad. And if for some single data point, similarly, if for some single data point, if we use simple data point to estimate like sample like 10 times, it's still very close to the true mean. Then we'll say it is good. It is reliable. It is robust. Right? Because no matter how we collect the data, every time we get a relatively smaller estimation error. Right? Smaller distance between our estimation and the true value.
How do we know this true value if all we have is the data?
No, we don't know the true value. So you really don't know the true value. That's the key issue here. So even we do not know the true value, we know that how can we measure the average distance between our estimation and the true value? How can we do that? Use the variance, as the gentleman just mentioned. Use the variance. Because their expectation, both the estimation method, their expectation are the true mean. So we use variance. So variance is what? Variance is so variance will be the expectation of the values that random variable can take, and the distance between the values random variable can take, and its expectation, that take square. So this is a very appropriate measure to investigate or to check the robustness or reliableness of our estimation. So now let us check the variance. So let us first check the variance for the sample mean. So what is the variance for sample mean? According to the definition, the variance for sample mean is variance of 1 over n, x1, x plus x2, up to xn. So this is the definition of the sample mean. And how can we compute this variance? We need to recall the properties of variance again. Right? So the variance is not as friendly as expectation. So first, how can we compute the variance of the summation of two random variables? Can we say it is simply equal to the variance of x plus the variance of y? Can we conclude this? No. Right. But for expectation, yes. But for variance, no. And when this equality holds, when does this equality hold?
To subtract the covariance.
Yeah, that's for general case. I mean, in what kind of cases the variance of the summation of random variables is equal to the summation of their variances? Excuse me.
If they're independent.
Yeah, if they are independent, right? So only when x and y are independent, if and only if x, y are independent. So this is the first property. So the second property is that the variance of the random variable multiplied with some constant. How can we compute this variance? Is it directly equal to say multiply the variance of x itself?
Squared.
Yeah. So keep in mind this is different from expectation because variance is talking about the expectation of a square distance. So the unit is different from the expectation. Therefore, here, when we calculate variance, say multiply x, we take say out, we must put a square here. So now we'll look back into our variance for the sample mean. So first, again, we treat this summation as a single random variable, right? So this is a single random variable multiplying with a constant. We first move 1 over n outside. Then what should we do? We move 1 over n outside, we take square, right? So this is 1 over n squared, and variance of x1 plus x2 plus xn. And how can we compute this? So generally, we can now assume the summation of x1, xn, the variance is equal to the summation of their variance. And how can we compute this?
Well, with the IID assumption, you know that what you're assuming is independent, so you can't just have the variances.
Yeah. Yeah, right? We need to use this assumption again. So now you can see how useful this assumption is. Because according to the IID assumption, x1, x2 to xn are all independent to each other. So now we can use this special equalities, right? So now we can safely do the summation of the variance for each random variables. And again, because x1, x2 to xn are IID, means that each random variable or each data point follow exactly the same distribution. So their variance are exactly the same. So let us denote the variance on the line, the variance for the distribution f is just VRF. Right? So we know that each random variable x1 to xn, their variance will all be VRF. So now it ends up with n VRF. So here we have n VRF. And now we know, because outside this is 1 over n squared. And now we only have n. So finally, what's the variance? Finally, we only cancel 1n. There's still 1n left on the denominator. So finally, the variance of our sample mean is 1 over n VARF.
So at this point, though, we still don't know what the variance of f is, or the expected value of f is, right?
No, we don't know. So now let us check another estimator, x2. Like use one single data point for the estimation. So what's the variance for x2? What's this? Yeah, the variance for f. Why? Because x2 follows f. Right? So variance is simply VRF. So now we can compare. Right? So this is variance of the sample mean, and this is variance for a single data point estimation. So whose variance is smaller? Obviously this one, right? As long as we have more than one samples, our variance is largely divided. So now we can imagine the difference of using the two methods to do the estimation. If we use sample mean, so suppose this is our true mean, yeah, right? If we use sample mean, the first time we get one estimation here, and next time we'll get here, next time we'll get here, and it won't be too far away. But if we use one single data point, what will happen? It can jump in a much larger range, right? Because it's variance, because this variance is much small, and this variance is much larger. So on one time, x2 could be here. Next time, x2 could be here. But occasionally, it could be here. Right? It is possible. But on average, obviously, x2 has larger distance from the true value.
So if you have enough data points, eventually you converge to the variance. Is that
It's not converted to the variance.
it's not converging, but it's like you're getting closer and closer to the true variance the more data you have. Is that
I think you're intuitively get something, but it's not very, very accurate. This is essentially what we're going to talk about in a minute, about central limit theory. This is talking about converges to something, but it's not about variance. So now I can say, because the variance for the sample mean is much smaller, so on average, we can say under many such kind of data set collection and estimation, we can say on average they won't be too far away from the true value. But if you use just one single data point, it's not as reliable as sample mean, because the large variance, it can jump much more wildly. So any question about this point?
So can we say the variant f is the cause of the data noise?
No. We're not assuming any noises in the data right now. Or you can say, okay, the variance contains some noise. But right now, we simply assume there follows some distribution. The noise could be contained in distribution. It is possible. We're just talking about how can we more reliably, on average, to get an estimation of the true mean for this hidden distribution. Any question so far?
Wouldn't the variance of x2 be 0?
What?
Wouldn't the variance of x2 be 0?
Yeah, if you assume, okay, we're observing some constant value, then seems not necessary because x1, x2, xn will be the same all the time. Right? Then there's no difference. But if there is some variance, we're talking about the random variables. Okay. So now we can see the rationality of using the sample mean to estimate the true mean of hidden distributions. So there comes another question. What's the distribution of the sample mean? So from our single data point estimation, right, using like x2 or using x4 to estimate the true mean, we know that the distribution of x2 is exactly the hidden distribution f, right? So now what about the distribution of the sample mean, namely the average of these data points? Will this distribution be the same as the hidden distribution f, just like x2? No, we are talking about distribution rather than some quantities. We know, okay, the expectation for this sample mean is exactly the same as the expectation for this distribution f, but that does not necessarily mean that they are the same distribution, right? They just have same quantities in terms of mean. Then the question would be, what's the distribution of sample mean? Looks like because they are simply average of a set of IID, random variables, coming from the same distribution, right? So intuitively, it looks like x should follow this hidden distribution f as well. Sounds reasonable, but it's wrong. Actually, distribution of x could be very, very different from F. I can give you a very simple example. So, for example, we're doing a coin result, right? So if we toss a coin, we have two outcomes, head or tail, meaning that this hidden distribution is just a discrete distribution, either head or up. Right? So now we can investigate the sample mean from the samples from this distribution, binary distribution. For example, if I have 3 samples, like 1, 1, 0, right? So what will be the sample mean? Yeah, 2/3, right? This is a continuous value. And our original distribution is binary. So obviously, our original distribution cannot describe a continuous value. So from this simple example, we can say, actually, the sample mean could be very different from the original distribution that sample or produce each random variables that are average. Then what will be the distribution of the sample mean?
Would it be normal
Yeah, that's a good guess.
for large N?
That's a good guess. That's our content about central limit theory. So central limit theory says, let me write it down briefly. So X is the average of a set of ID random variables, and we know that x1, x2, x3, ID, and x1, x2, to xn, they follow exactly the same distribution. And central limit theory actually characterizes what's the distribution of the sample mean. It says that the distribution of this sample mean will become more and more like a normal distribution, with mean being the true mean for the F, the hidden distribution, with variance being the variance for the F divided by the number of samples. So it means that as long as we increase the number of data points n, and the sample mean, its distribution resembles more and more this Gaussian distribution, this normal distribution. And in mathematical terms, it says it actually converges to this normal distribution. But convergence actually has many meanings. In the mathematical literature, it could be convergence in distribution, convergence in probability, converge almost surely. Here we won't explain the detail, but I just want you to build up a concept. This is a kind of dynamic trend. So when you increase the number of samples, the distribution of the sample mean becomes more and more like a Gaussian. But this Gaussian, it resembles has smaller and smaller variance. So you can imagine, right? So as long as you increase the number of samples at the beginning, this is a Gaussian, right? And the distribution of your sample mean would be like this. It's different from this. So let me write it in a different style such that you can see it clearly. So this is the Gaussian. It resembles, but when an n is smaller, their difference would be obviously. So this could be the distribution for the sample mean. But when you increase the number of samples, like n to be quite large, and the Gaussian it resembles becomes much, much thinner. Right? So it could be like this. Because variance is small. But at the same time, the distribution of the sample mean looks closer to this Gaussian. For example, it could be like this. nearly overlap. So you can say two meanings from the central limit theory. First, from the look of distributions, when you increase the number of samples, it looks more and more like a Gaussian. But finally, you can imagine it finally overlaps with a Gaussian distribution, a normal distribution. But at the same time, the distribution, the Gaussian distribution, it looks like has smaller and smaller variance, meaning that it is thinner and thinner. The bell is thinner and thinner. Does it make sense?
This is just assuming the hidden distribution was a Gaussian.
No. No, that's something I want to emphasize. This conclusion has nothing to do with the form of f. That means no matter whether your f is indeed a Gaussian distribution or not, it could be a discrete distribution, like just a binary variable, 0.3 and 0.7 or 0.5, 0.5. Doesn't matter. It could be a uniform distribution. It could be the Laplace distribution. It could be the gamma distribution, whatever distribution. As long as you calculate sample mean, you check its distribution, you will find the same trend. So this is kind of striking properties in the central limit theory. That's why how normal distribution connects to almost all kinds of distributions. So now to see this effect, I want to show you some demo. So let me find it. I really hate this kind of things because every time I will try multiple times until it fixes. I still don't know how to do it succeed once.
How many times do you try?
Usually 3 to 5 times.
Is it enough?
This is my average performance. The variance is small. Oops. Okay, can I see it clearly? Looks like it's too big. Is it okay for everyone to see it? Or I can enlarge it? It's good. It's good? Okay. So I won't go through the detail of this code, and don't worry, you are not required to do some homework on top of this code, but you are welcome to modify this code and check what I said. You can replace the distribution here. Here we'll use uniform distribution for the illustration, but you can definitely replace it with any other distribution you like, and look at whether you can see the trend as we just mentioned in the central limit theory. So let me just briefly go through the code. So the first 3 lines is just the import the necessary library to generate to sample the random variables, to generate random variable samples, and also these two libraries are for the plotting. And this function is simply to calculate this called plot distribution. It's actually not plot exact distribution. It's actually to plot a histogram of a set of IID points. Why would we plot a histogram? Because actually we don't know. Sorry. So actually, we don't know the distribution of x bar, the sample mean. Even I know the original distribution, it's really very hard to compute the probability density for this. Then how can we investigate its distribution? How can we do that? A commonly used method is called histogram plot. So if I can produce a set of IED samples for this random variable, anyone can see it here? Okay. Suppose we got a set of data points follow the same distribution as x bar or any other distribution, whatever. Okay? And the histogram is produced as follows. We just generate a set of bins to separate these data points. These bins are usually equally spaced. For example, it's like this. So obviously, for some high density region, we have more data samples in some bins. And for low density regions, we have less samples. For example, if our distribution for this is a Gaussian, right? We know for the Gaussian distribution, in the bins surrounding the mean, we have a high density. So we could observe a lot of samples inside those bins. And for those bins which are far away from the mean, so this is a Gaussian distribution, we can only observe a small number of samples in the bin. Okay? And then to draw the histogram, we simply count the number of data samples inside this bin, and then plot the histogram which proportional to the number of count. So we can divide the count by the total number of data points, or not, whatever, doesn't matter. Right? So obviously, the more likely, the larger count the bin, the higher the histogram you get. And finally, from the shape of the histogram, you have a rough look about the original distribution. So we can investigate the distribution of the sample mean in this way. So meaning that every time, okay, I do it like 1,000 times, and each time I collect a data set, calculate the sample mean, we got one sample, right? And then I collect another data set, I got another sample mean. I do it again, like 1,000 times, so I get 1,000 samples. I will bin it, and then compute how many samples fall in each bin, and draw the histogram. And we'll say whether this histogram looks like Gaussian. This is a way we investigate whether it becomes more and more like a Gaussian. Any question about this? This is a very commonly used way to investigate some distribution, some unknown distribution. Okay. So this function is doing the histogram plot. Why disappeared again? Okay. So this function is just to draw the histograms for a set of IID samples, which are in this array. This is a list of data points. And the title is just some parameters control the title of the graph, and the bin mean and bin max indicates the lower bound of the bin and the maximum bound of the bin. So we can just escape it, and we just draw the bin between 0 and 100. So this is a setting of min bin and max bin, and we create 50 bins. These bins are equally spaced to produce the histograms. And how many data points we draw for the histogram? 1,000 times, 1,000 points. We believe that 1,000 points have already are sufficient for you to look at the trend. But of course, we can modify the number of trials like to be 10,000. We can see it more accurately. And here we assume the original distribution f But in our IID assumption, each data sample follows F, right? Here we assume this F is simply a uniform distribution between 1 and 100. So what is uniform distribution? Meaning that if I specify the uniform distribution, say between 0 and 100, meaning that x can take any value between 0 and 100, and the chance is equal. So to see it, how this uniform distribution is different from the normal distribution, let us first look at the distribution for the uniform distribution. So here we just copy this. Copy here. Sorry. Use the word. So here, sample distribution is generated from the uniform distribution, and we just plot. It's a histogram. It's actually not histogram. It's just the PDF. So here is the result. So we can see this is the uniform distribution. You can see that the value of the random variable takes between 0 and 100 are totally equal likely. And now, let us check. If we do the sample mean, here n values indicates the list of number of samples in sample mean. So here n equals to 1, meaning that every time I only sample one random variable and take the average. It means that we will almost do nothing, right? The sample mean will follow the uniform distribution. And let us look at when we set n to be 1, meaning that your IID samples are only contain one single data points. What will be the distribution of the sample mean? Here, let me just command the original distribution and run it. So you can see with n equals to 1, the sample mean is far from Gaussian, right? Why? Because n is only 1. The trend for Gaussian is obvious only when n becomes larger and larger. So obviously n equals to 1 is not indicative. So now let us set n to be 2, right? Meaning that, okay, every time I just sample 2 IID uniform distribution random variables and take an average. And I want to look at how this average of 2 uniform distribution random variables will distribute. Will it be very different from uniform distribution? Let us take a look. Run it again. So now, what can we see? What can we find? This is obviously not uniform distribution. Very different from uniform distribution. Obviously, we can say the chance that the sample mean, which is on average over 2 uniform distribution random variables, has larger chance to appear in the middle, right? And much less chance to appear in the 2n. And now we can further increase n, like to be 10. So what can we observe? it even resembles more like a Gaussian, right? But at the same time, what will be the Gaussian? What's the change of this Gaussian? The variance becomes smaller, smaller, right? Because you can see this if you draw a curve, a PDF curve, like covering this histogram, you'll say, okay, this bell is kind of narrow, much more narrow than the case that I'm two. Right? And again, further increase the number of samples for the sample mean to be 50. So now we can say it's an even more narrow curve, right? And actually, here we cannot quantify, but actually it is even closer to a Gaussian distribution. So we can run them together to see a trend, and also we can contrast with the original distribution. So now we run it again. So now this is the original distribution where each random variable is sampled from. It's a uniform distribution, which is very, very different from normal distribution. And we look into the sample mean. If we take the sample mean over just one sample mean, that we actually do nothing. You can say the distribution of the sample mean won't change much. So it's still far from Gaussian. But as long as we increase the number of samples to average, become 2, you can see it's already delays much from the original uniform distribution. And now when we increase the number of samples in the sample mean, we can say it becomes the distribution of the sample mean becomes more and more like a Gaussian. By Gaussian, it resembles more and more narrow, indicating the variance is smaller and smaller. And here we only stop at n equals to 50, but you can continue to investigate. And this code is shared in the course material, and you can download from the course website, and you can try to type this piece of code in your Python IDE, and you can simply revise the code here. Here is a create uniform sample distribution, right? You can obviously write your own function like create a binary sample distribution. You can create Laplace sample distribution, and then you rerun the code, and you will see similar trends. This is something amazing from the central limit theory. Okay, so we'll stop here today, and on Wednesday we'll begin to introduce because we use this sample mean to estimate something we want, right? This sample mean is a random variable. So if we want to generate some guarantee about the error of our estimation, what's the distance between this and the true value, we cannot say it for sure, it's 100%. We need to account for the possibility, the uncertainty, right? Now how can we account for the uncertainty to derive a guarantee of the error? That is called probably approximately correct PAC framework, which is based on several commonly used concentration inequalities, which we'll discuss further on Wednesday. Okay, see you on Wednesday.